Hello, everybody. So we've started in the last video to go beyond NP. We got to CoNP, and we're going to continue with that to find harder and harder problems within what we call the polynomial time hierarchy. And for that, we have a returning visit of oracles. By the way, did you check which is this oracle? Well, if you didn't, then this is the oracle of, or at least a depiction of the oracle from Delphi. For those whose classic education is strong. And we'll talk about these classes that you can define with oracles. And this will be actually pretty interesting and useful. So how do we think about oracles? We discussed it before. Think of them in terms of Turing machines, subroutines. So an Oracle Turing machine M with Oracle B lets you include the following statement within your pseudocode. If Z is in B, so you query for Z, then you do something, otherwise you do something else. So think about it like you have a library that includes the function B. So if Z is in B, and you can just invoke it with the cost of one step. So Z is, of course, something you compute before. And as I said, this is something that you can verify in one step. And we already, so the confusing thing about how we use oracles in this class is that sometimes we use oracles to languages that are very hard, in particular ones that are not decidable or not recognizable, or even worse. This is what we had in the hierarchy of undecidable problems, the arithmetic hierarchy. Here we will still do it with languages that are perhaps not in polynomial time. They're decidable but not in polynomial time. And that makes it a bit confusing, but it helps us understand the structure of languages that are harder than NP problems. So some complexity classes with oracles. P, so P for polynomial time with access to B. P to the B is all the languages that can be decided by some polynomial time Turing machines that have an oracle for B. That applies for any function. For example, P to the SAT are all the languages that are decidable in polynomial time with an oracle to SAT. If I give you a SAT oracle, what can you solve? P to the NP, so here NP is a class, is the class of languages decided with some polynomial time oracle machine that has some oracle in NP. So instead of just being stuck with the SAT, you can use whatever oracle you want. Perhaps you want perhaps you want click, so you can have an oracle for click instead of the oracle for SAT. So is psat contained in P to the NP? Is P to the NP contained in psat? Well, yes, psat is definitely contained in P to the NP. This is by definition because P to the NP, you're allowed to have access to any oracle in NP. How about P to the NP and contained in psat? This is true as well, because every NP language can be reduced to SAT. So if you have a machine that has oracle to click, you can simulate it with an oracle to SAT. You don't need an oracle to click. You can, whenever you're asked for some query about GK, whether it is in click, you reduce it to a formula, and you ask your oracle for SAT. So with an oracle to SAT, you can solve anything that you can do with any other oracle in NP, and therefore P to the NP is contained in P to the SAT, or they are identically the same. Right, so for every polytime Turing machine M with oracle B to NP, we can simulate every query Z to the oracle B by reducing Z to the formula phi in polynomial time and then asking an oracle for SAT instead. P to the B are L that are decided with a polynomial time Turing machine with oracle to B. What happens if B is in P? So P with an access to an oracle which in itself is in P. Is P to the B contained in P? Yes, because whatever the oracle tells you, you can compute yourself in polynomial time. So you can simulate the you can simulate the oracle by yourself in polynomial time. So for every polytime Turing machine M with oracle B to B, you can simulate every query Z to the oracle B by simply running the polynomial time decider for B. And the resulting machine runs in polynomial time. So this is just like you run your library, but now when you combine the algorithm for running a procedure from your library with your own algorithm together, they are still polynomial time. Is NP contained in P to the NP? Yes. You just ask a single query to the oracle and you solve your problem. So if you have L in NP, you just define an oracle Turing machine M with access to L. You can just have an oracle to L, which is in NP, and you just ask the oracle for your input. So you want to ask if you want to see if X is in L, you just ask your oracle, is X is in L, and you can output it. Is coNP contained in P to the NP? That's more interesting. The answer is yes, still. Again, you just ask the oracle for your answer, but now you're going to switch the answer. And that's again this point that I've been making again and again, that an oracle that's always right is this that's always wrong is just as useful as an oracle that's always right. So for every L in coNP, we know that not L is in NP. So define an oracle Turing machine M with access to not L, which is in NP, which asks the oracle if the input is in not L. You accept if the answer is no, and you reject if the answer is yes, because if the answer is no, it means that the input is not in not L, meaning that it is in L. If the answer is yes, it means that the input is in not L, which means that it's not in L. So more generally, we have that P to the NP equals P to the coNP, because you can simulate every algorithm that runs with access to some NP problem by an algorithm that runs with access to the co-problem, and you just reverse the answers, and vice versa. NP to the B are all the languages that can be decided in polynomial time non-deterministic Turing machine with an oracle for B. CoNP to the B are all the languages that can be decided by a polynomial time non-deterministic Turing machine with an oracle to B. Is NP equals NP to the NP? Is co-NP to the NP equals NP to the NP? So both of those are open. For example, if although we suspect that in both cases the answer is no, we don't know it. Because, for example, if P equals NP, then all of these classes and the classes that we're going to find above them, all of them collapse. This is what's known as the polynomial time hierarchy collapsing. Again, something that bothers complexity theorists and not the entire world, but still. So it is believed that the answer is no. Believes that NP with oracle to the NP, you cannot simulate it. It's not like P with oracle to P that you can simulate it, because in particular NP to the NP allows you to answer co-NP problems, right? NP to the NP contains co-NP, and if they're equivalent, it means that NP, if there is inequality here, then NP would equal co-NP, which we don't think is true, or at least that, yeah, with NP algorithms you can solve co-NP problems, because with NP to the NP you can solve co-NP problems. And similarly, we don't believe that co-NP to the NP equals NP to the NP. I want to show you one example of a problem that exists in these. Still, these are, so we can of course continue this forever. NP to the NP, NP to the NP to the NP, co-NP to the NP to the NP, and so on and so forth. I want to show that at least in the low level of this hierarchy, there are interesting problems. So I want to show that logic minimization is in co-NP to the NP, and we don't know how to squeeze it below. So two Boolean formulas, phi and psi, over variables x1 to xn are equivalent if they have the same value on every assignment to the variables. Any assignment that satisfies phi satisfies psi, and vice versa. So are x and x or x equivalent? Well, yes, this is easy. Whenever x is true, then both of them are true, and otherwise both of them are false. Are x and x or not x equivalent? The answer is no, because the right side is tautology. X or not x is always right, whereas x can be false. How about this formula? Is this equivalent? Well, if you think about it a little bit closer, you'll see that the answer is yes, but it requires already some thinking, and it's still a very short formula. And you can see that when it becomes longer and more complicated, this is not obvious. So answering about equivalences is not easy. The Boolean formula phi is minimal if there is no smaller formula that is equivalent to phi. So this allows us to define this notion of mean formula, which are all the formulas that are minimal. So we're going to argue that mean formula is in co-NP to the NP. We cannot show that it is not in anything simpler, because we don't know that, for example, if P equals NP, all of them are in P, but that's what we know. So naturally it's in this class. So for that we define also the following language, non-equivalent, which are phi and psi, such that phi and psi are not equivalent. Observation, not equivalent is in NP. Why is this correct? There is a very easy witness that two formulas are not equivalent. It is an assignment that satisfies one and not the other. Now we want to show that co-NP with oracle access to not equivalent can solve mean formula. This will mean that co-NP to the NP can solve mean formula, just because non-equivalent is in NP. So given a formula phi, try all formulas psi that are smaller than phi, and if phi psi is in non-equiv, then accept, otherwise reject. So, so note that this for all formula is a Cohen-P algorithm, and this Cohen-P algorithm needs to ask these questions: is phi psi in non-equivalent? So it is a Cohen-P procedure that asks oracle questions to a non-equivalence which is in NP. Now, why does it solve mean formula? Because a formula is minimal if there is no smaller smaller psi that is equivalent. So and this is what we're checking here. So mean formula is not known to be in Cohen-P. It is in Cohen-P to NP, but we don't know that it is in Cohen-P. And it shows that, at least based on our current state of knowledge, these languages, these classes are actually contain interesting languages. So let's kind of summarize our knowledge so far. We'll get even further in the next video. We have P, we have NP and NP complete problems, Cohen-P and Cohen-P complete problems. We have P to the NP, which contains all of those. P to the NP contains P, obviously, but it also contains NP and it also contains Cohen-P. NP to the NP contains all of those. It definitely contains P to the NP, which contains all the rest. And we have Cohen-P to the NP, which contains the mean formula. And in a sense, this kind of mimics the picture we have before. So if we have P, NP, and Cohen-P, now we have P to the NP, NP to the NP, and Cohen-P to the NP. And now we can continue. We can have P to the NP to the NP, and NP to the NP to the NP, and Cohen-P to the NP to the NP, and so on and so forth. And the hierarchy that I'm discussing is doing that for any constant number of times. This is known as the polynomial time hierarchy, but we will save you all the levels of this hierarchy beyond that. We'll just say that all of these problems are still decidable. We're actually going to show that there are even, we'll show a more concrete upper bound on them. So all of these problems, all of this beautiful picture is just in the most simple class that we had in chapter 2 of our class. So all of them are the easiest from the point of view of computability, but some of them are definitely quite difficult when you think about efficiency. Beyond that, we have undecidable. So we discussed the first levels of what's known as the polynomial time hierarchy. It contains many interesting computational problems, and there is a lot that we don't know about it. We don't know if this hierarchy contains new problems whenever we go up in that, or at some point perhaps it collapses. So at some point you don't get anything beyond